Okay, so chapter 3, process concept. Now we're getting into more the theoretical part of the course, which is the main part of the course. And we're talking about processes. What is a process? So we mentioned what a process. What's a process? Something called. Yeah, a code that's running. A program while running. So we're going to talk about that. The objectives: to introduce the notion of a process, to describe the various features of a process, to explore interprocess communication, to describe communication with client services. Process concept. An operating system executes a variety of programs. Batch system, time system. So it's something called a batch system, which the best example of a batch system is like a printer. If you just think of the printer itself, you can send lots of jobs to the printer to print. And you'll print them one by one. You may send a job and it won't get printed right away because there's other jobs first in line. So that's kind of a batch system. You do things all at once. You do things in one after the other. You can also have time sharing, where the time, you have a time limit. You say you print one job, you print one print. Now that usually you don't stop printing in the middle. But for other types of activities, you can stop in the middle. Let's say you're calculating something. You could stop calculating this and now go to the next process and do some other thing. So in other words, the CPU can be divided by time. That would be called time shared system.
Wait, what's batch again?
Actually, we do one after the other. And we don't start the next one until we finish the first one. Processes. And time sharing means no, we interrupt in the middle and we interleave. We interleave processes based on a fixed time slice. We don't let any process have the CPU for more than a certain time slice, 10 or 20 milliseconds. Now, usually the word job refers to like a print job, right? And which is batch. And tasks are usually things that are in a time sharing system, but is a textbook use of the term job and process interchangeable. Not really much of a difference. A process of program and execution. Process execution must progress in sequential fashion. Right, they go forward. Multiple parts. The program code. So we know this from our course in MIPS, in system in computer architecture. There's the text section. There's the PC, the program counter. There's the stack. What's the stack for?
Functions.
Functions, right? All of our function information is in the stack. The data section. What's the data section for? Well, let's read the code. The data section. What's the data section for?
Like what you actually wanted to send.
Right, what data you're working on. It could be the array. An array or global data. The heap, what's the heap? Heap we never use. But the heap is when you do new. It's also part, it's like beneath the stack. We never did that. But
What's
dynamic, it's where your program will reserve dynamically allocated memory. The program is a passive entity stored on a disk. It's an executable file. It's just sitting there. It's passive. The process is active. It's a running program. It has to be loaded into memory. You can't execute a program inside of memory. Execution. If you're in a GUI system, you'll run a program by clicking on it. If you're in a command line operating system, you will or interface, you'll type the name of the program and hit enter. One program can be several processes. How can that be? We said a program in running is a process. How can one program be many processes? What? Right, it can be doing more than one thing at the same time. So we're going to learn there's a system called fork. which creates a second process. So that you can have two processes running simultaneously. Of course, they'll only really be running simultaneously if what's in the hardware.
It creates another process.
Two CPUs.
Two CPUs. You have to have at least two CPUs or two cores in order to really have a multi-process program. Yeah, Naomi?
What the fourth, it creates another process?
The fork creates another process. That's the system called create process. Okay. And here you have this picture. You recognize that picture from data
from-
structures, from
Architecture.
architecture. You see the stack goes down, the heap goes up. The heap is the dynamic allocation. The data, the text. That's every process has all this in memory. So it's a process in memory. In other words, go back to your computer architecture. That program that you had there, which had its own stack and so on. Imagine now on one computer, many of those. So now, this goes back to what we said earlier, a few minutes ago. What's the kernel space? In other words, this is the process space. Think about it. This is the space in memory for that process. Every process has its space. Now, a process can have also a state. This is a state is a concept that's maintained by the operating system. The operating system will know what state each process is in, and it will be useful to the operating system to manage. If it, in other words, if you think of the state as like your coach on your basketball team, so he knows what state, who's injured, who's ready to go out on the field, on the court, you know, who's not there at all, who died, well, they. So you have these states. New, the process is being created. So that's like the guy's getting on his gym shoes. You can't put him on the court yet because he's new, but he's about to be ready. Running, he's actually on the court. Waiting is he is, let's say, he hurt his knee, and so the doctor is, bandaging up his knee. He's not ready to play. He's waiting for some external event to finish, and then he'll be ready again. So waiting for a process would be like he's waiting for I/O. That's the normal thing you wait for.
Is it also, could it be waiting for like the timeshare?
No. That's exactly what it's not. No, it's waiting for an external event. In other words, something that the operating system is not itself controlling. Like a person to type, I say, please enter your 2.0 number. And now the computer goes into CN and it's waiting. And I have to type. And I may scratch my nose for 5 minutes before I type in my 2.0 number. And even when I do type it in and they hit enter, now he's got to read the number 1, 1, 3, 4. Got to read those numbers. That takes time. All that time, the process is just doing nothing. He's waiting. It's like the doctor is bandaging up his knee. He's still, he's not injured, but he's incapable of proceeding forward until the I/O, until the keyboard has given him all the data that he's interested in. That's waiting. Ready is the process is. See, look at the next term. Read that sentence. Process is waiting.
It's the same thing,
It's the first 4 words are the same,
but it's waiting to be
but it's totally
assigned to a
different. And
process.
what was your name?
Abigail.
Abigail. So Abigail said, what if he's waiting for the timeshare? That's exactly this next one. He's waiting to be assigned to be assigned to a processor. In other words, he's waiting for the operating system to give him a slice of time. That's the waiting that you're thinking of. So it's called ready. Because he's obviously waiting. Also, he's ready and waiting. He's ready and waiting, as opposed to regular waiting. It should be like called not ready and waiting.
So would it be like, waiting for, let's say, let's say like to sign up for us, to play a certain sport, waiting for it to come online so you can play in it, and then the ready to be waiting to receive your team, basically? Because you're waiting for
In my mashal, you're saying?
yeah,
In my mashal, ready would be that he's on the bench, he's got took his sweatshirt off, his warm-up suit off, and he's ready to go on, but there's still 5 guys on the court. He's waiting for the coach to do a player switch. assume all of your girls play basketball in high school.
So what would the waiting one be on my show for?
Waiting is, like I said, he's being taped. Coach is taping. You know, they do that in sports.
What do you mean?
I just learned about that. No, the coach tapes him. You know, they put like something to protect. You ever see athletes that have like this black tape?
Yeah.
So they're taping him. They're putting tape on his shoulder, on his knee, but he's not ready. He can't go out yet because they're still taping him. He's not ready.
No, I
The
understand.
doctor is bandaging his knee. He's right. He's not ready yet. He's waiting for somebody else to finish preparing him. In the Nimshal, it's in our example, it would be he's waiting for the keyboard to give him some input. And terminated, the process is finished executing. Now you can say, well, why is terminated a state? If he's terminated, he's not, it doesn't exist. The process that's dead is not a process anymore. So he could hang around actually in a terminated state, because it could be that, for example, his parent wants to know if he's terminated, but he doesn't want to know right now. He wants to know in 5 minutes. Did that son ever finish? So the operating system keeps track of him for that he's finished, to know this. Of course, also there's I think that's part of the explanation. I think also part of the explanation is it may take the processor time to relinquish his memory, right? If he's terminated, although actually if he's terminated, he doesn't have any memory. He's actually terminated. He's no longer got this process and memory picture. You know, he lost that. That picture has been deleted for him if he's terminated. He's not taking up space there. See, a waiting process is taking up space in memory. All right. So here's like a diagram of the states that a process can go through. You see, from new to ready, and then from ready he goes to running. That's when he's actually on the court playing basketball. Now he could go from running to exit and can terminate. You see terminated on the right there? Or he could go from running to waiting. He's waiting for the coach to bandage his knees, waiting for the keyboard to do. And then once he's finished waiting, he doesn't go back to running. That's the main point to see in this diagram. He doesn't go back to running, he goes to ready now. Now he goes back to the bench and he's ready, because when they were bandaging him, they put on another player on the field now. The coach is gonna have to decide whether to replace him. Okay. Interrupt, what is interrupt? It could be interrupted. Interrupted means a signal was sent to him to stop. And then he goes to, for whatever reasons, we're not explaining it. Notice it says, on the arrow from waiting to ready, it says IO or event completion. That means he was waiting for the IO to finish, and now it's completed, so he goes to ready. Notice on the arrow from ready to running, it says schedule and dispatch. Well, that's what we're going to talk about. The process scheduler dispatches him. It means puts him on the field, puts him on a basketball court. He says, okay, you can start running. And what is interrupt? He got it. What would stop him from running that wouldn't be because he's waiting for an IO event? Some other kind of event, some other kind of interrupt. Could be the operating system itself interrupted him and told him, your time is over, somebody else is going on.
Polling versus.
Yeah, we talked about interrupt, we talked about polling. Interrupt just means any event that happens because of a occurrence, because of something in the real world. That real world could be a time event, like 10 milliseconds pass. Or that real event could be somebody pressed Control-C on the keyboard. An interrupt is some real world event that enters into my programming world. The programming world is sequential. Event, I just go according to the program. But interrupts are unpredictable events that come in from outside of the program. So here it is the operating system comes at time is elapsed, stop. Okay, now there's something this is very important, PCB. Not PCP, PCB. It's the process control block. It essentially is the that's a hoot, the all of the operating of the process, or maybe even better, it's all the information necessary to describe and define the process. What describes and defines the process? Well, his state, we just said. What state is he in? Is he ready or not? That's the first thing. What's his process number? So everybody has an ID number. His program counter. Where is he in his execution of his code, right? That's the program counter. Is he on the first line or the 100th line? Registers. What are the values of all the registers at this moment? You know, memory limits. Where does his memory start and stop? When we said memory, what do we mean? We mean again this picture. This is his memory, right? The process in memory. It has a 0 at the bottom and a max at the top, but it doesn't have to be a 0 and a max. It could be like starts at 100 and ends at 200. Wherever he stops, those are the limits. So we need to know where is he in memory. And then we have to have the list of open files. Now there's all the files that he opened. It doesn't have to be, I disagree with it a little bit. It's not just files. It could be anything that's what we call operating system resource. What are operating resources? A resource means can I ever go to a resource room in school? What was in the resource room? Resources. What were the resources? Paintbrushes, maybe, and a computer, I don't know. Different paper. Resources are stuff that you can use to do stuff, to accomplish goals. So files is a resource that the operating system provides you. As a program, you need a file, it'll give you one. But you can also have other things which we mentioned, types, which are like files in memory. There's also something called shared memory. So any of those things that he has associated with him are listed there, along with their ID numbers. Once you have all this information in the PC, what can you do? You can essentially stop the process for an indefinite amount of time and then start it up again. Because you could even clear out the registers. If you stored all the register values and the program counter and the process number, all that information in a database somewhere external, now I can clear out all the registers, I can clear out the program, I can put another process into memory, into the registers, and run him. So this is what allows us to do CPU switch from process to process, which is called a context switch. This is a hugely important concept in our course, called a context switch.
Context switch.
Context switch is where you. No, but we have how many minutes? 1 minute. A context switch is where you switch one process from being in execution to another process being in execution. But in order to do that, you need to switch his context. What does it mean, his context? It means all this information. You have to take out of the registers all the register values from the one process and put in all the registers of the new process. You have to replace so that now the CPU can run that. Imagine your MIPS program. You have 2 MIPS programs now. You have one running, and in the middle he did 5 lines, but he didn't finish the program. Now you stop him, you copy out all the data from all the registers and the PC and everything, and you put it in another process and run him. Now in the meantime, where are you going to store that data? You have to have a database or on some kind of memory location. The operating system will maintain a linked list, like you learned in data structures, right? The operating system will maintain a linked list of structs, where each struct is a PCB, is all that information that describes accurately that process. That's what enables you to swap him out of memory. And that's what this picture describes here. See, it says save state into PCB 0, reload state from PCB 1, And now I loaded it into, and I can start executing. So in other words, process 0 is running. Then the operating system jumps in. Yeah, let's look at this picture for a second. Picture. Process 0 is running. Then the operating system says, time's up. Save the state to PCB, do whatever, copy, do some other things, which it's not telling you about, and then reload the state from the other process, PCB1, into memory, and now I can start running him. Now stop him and go back to him. Now you'll notice that we lost something very important here. We have an idle time, right? This amount of time the operating system needs to take to stop this process and start the next one. That is the overhead of the context switch. This period is while he's doing the context switch. He's switching from one process to another, and he's losing time. Hopefully, this idle time will be small, and this execution time will be big. That's how we do time shift. I will stop here.